Okay guys, we're going to continue with 1258. In the previous video we saw how we had the VT curve and then we obtained the position time curve. Okay, so go and look at that one. In this one we're going to, so we had the VT, we got the ST curve, and what did we do? We had to integrate the VT curve essentially to obtain the position time curve. We had to integrate. So recall, if we've got position and we want to get to velocity, we need to differentiate. Velocity to acceleration, we need to differentiate. Acceleration to velocity, we need to integrate. Velocity to position, we need to integrate. Okay, but this is really strictly true only if these are functions of time. Okay? Only if these are functions of time. When it becomes functions of position, recall we have ADS equals VDV. When we have functions of there is still functions of position and there's no time value, or there's no function of time, there is still the matter of differentiating and integrating, but it's not as clear cut as this. Okay. Okay, so just take note of that. So position time to velocity is differentiate, to acceleration differentiate, reverse we integrate. Okay, so we have velocity time, we want acceleration time. Let's just redraw it again. Redraw it again. Is that redundancy? Redraw it again. Okay, so let's redraw it, or let's draw it again. So if we've got, there's our velocity time curve. This was a function of t cubed. So it was 4.8 10 to the minus 3 t cubed. And that was minus 3t plus 150. Okay, again, erratic motion, piecewise function. Okay, so again, what do? We break it up. Here's our AT curve. We break it up between 25 and 50, 25 seconds. I'm sorry, between 0 and 25, that's what I was trying to say. We know A is equal to dv dt. So now, the previous problem, this problem here, we had Vt, and we wanted ST, so we had to integrate the VT curve. Now, we have VT and we want AT, so we have to differentiate VT to get there, okay? So what is the function of, what is the velocity function over that time period? It is 4.8 10 to the minus 3 t cubed. Okay, so acceleration is equal to 3 times that, if I recall, was 14.4. Let me just see my notes. 14.4 10 to the minus 3, and then that was t squared. Okay, there's my function. That is my acceleration function over that time period. Okay, and again, what you notice is if we're moving from velocity to acceleration and we have a cube function, we're going to have a squared function here. If there we had a linear function, say just v equals t, whatever, then here we would have a constant. Okay, so you need to also just check if your answers are right by using that kind of logic. Okay, but then what is a? So first of all, again, get our function. A is a function of time. Then you can plug in to try to find the actual value of acceleration at a certain time. So what is the acceleration at t is 25. Acceleration is what? 9 meters per second squared. We take that 25, we plug it in there. Okay, so we got a function and we got the value. Let's now look again between 50 and 25. 50 and 25. Again, acceleration is dv dt, ddt of, now what is the function in during this time period? It's minus 3t plus 150, minus 3t plus 150. So our acceleration is minus 3 meters per second squared. There is my function. A is a function of time, but not really a function of time. There's no time, but there's my function. So Here's my acceleration time curve. Remember, there's my velocity time. Here's my acceleration time. The function during from 0 to 25 is 14.4 10 to the minus 3 t squared. And the function I didn't draw this that well. And then what is the second function? It's just a constant minus 3. So if there's minus 3, there it is. And what's the value there? It's 9. So that's not a 9, that's an acceleration. That's 9. And this is time there, acceleration there. There's our function. So during the first 25 seconds, we are accelerating quadratically. And then during the next 25 seconds, we are decelerating at minus 3, a constant minus 3. Okay, and that makes sense, right? Because a linear function of velocity should give us a constant. And what is the slope? The slope is minus 3. And so we get minus 3 over here. Okay? All right, guys, so good luck. Hopefully this helps. Use this together with the examples that we did in class, which are the textbook examples. And do as many of these problems as you can. Okay? Good luck. Cheers.